Welcome back to our small series on how to build a digital pedal. In the first part, we got the basic concept and which hardware do you need or not. And in the first video of the second part, we actually installed Jack D and Port Audio to be able to get some sound from your USB audio interface into your C or C++ code. Thanks to it, at the end of this video, we managed to have a few sounds. This is the default PA Fuzz example, which is a slightly fuzzy sound. Before expanding it, making it easy to modify, for example, by allowing some parameters to make it less fuzzy or more fuzzy actually, I will take some time to explain this code. As I mentioned before, you don't need to know C or C++, but a background in programming would be nice. But I will focus on what's the difference here and the C and C++ specifics. You can also read the comments in this example file, or the other example, or the API reference. But for now, let's start it. Here is the first callback, which we modified a bit before. Remember this name, we will see it in a bit. Here is the main. In C and C++, the main is the entry point of your programs. We will use this function to set up a few parameters or other things and start our audio processing stream. We have here input parameters and output parameters. You may remember them from this. We modify the default device from input and output, and also I modified the channel count for the input device, which once again may change depending on how many input channels you have on your audio card. Now we modified those objects and we will open a stream. We create the stream variable a bit earlier. Here it's a pointer and we are passing it to the PA OpenStream function. We are passing this stream, some input and output parameters, but also some global parameters such as the sample rate and the amounts of frame per buffer we want to use. This will open a stream and modify the stream object internally by Port Audio. Lastly, the last parameters we need for now is the first callback. In programming, a callback is a function you are giving in parameters to another function. This way, when Port Audio will fetch some audio from the audio interface, they will call our callback to give us the opportunity to read the input and eventually fill the output buffer. Roughly speaking, it means that the callback will be called, giving us what's in the microphone of the audio interface and giving us the opportunity to output some sound to the amplified or to the headphones jack of the audio interface. For us, it means that input buffer is your guitar and output buffer is your amp or other pedals, of course. And lastly, we have this NULL. NULL is an absence of pointer in C, and it means that we are not giving anything. But what we could give here is some user data. It's a bit specific, but it's a pointer on void, and it basically means that if there is some data you need from within this callback that comes from some other place in your code, for example, you could have some C++ class with configuration and the value of your fuzz and how many milliseconds for your delay and some other things like that. Chances are you want to pass it via user data. This way, you will just, instead of null, give the instance to your class or to your struct. But for now, we don't need it because for sake of simplicity, we will in this tutorial use global variables to keep it simple. Now, our stream is open, but it's not started yet. That's what we are going to do now by calling PA start stream and giving our stream as parameters. Once this function is called, it's all started. Port Audio will start calling our callback with input informations. It's perfect. But one thing you need to know is that it's not blocking. We are calling this is in another thread, which means that it actually will pass this line, even if this is started. That's why here they inserted hit enter to stop program, because without this line, this line in C is actually waiting for a char, waiting for some user input. That means that when you click enter, this line will go to the next line, and then the program will terminate. If you don't put this line, you will have no sound because your program will terminate instantly, and the stream will not do anything at all. So now let's go back to our callback for a second. What we have here, we do have a void input pointer input buffer and pointer on void output buffer. Here we are actually casting, we are converting those input and output buffer to a sample pointer. What is it? Well, here sample is a type def to float, which means that sample is float. But it might not be super clear for now, so for the sake of simplicity, we will remove that and actually remove sample by float. And now our callback function is receiving two void pointers, and we are converting it to float pointer and a const float pointer. This is our guitar, this is our amplifiers. And this is not useful for now, but you may want to know that normally we are supposed to compile our programs with extra flags which make every warnings errors. In C it would be good practice, and in C it's an error not to use a variable. So here we are not using those variables in our code, so by using this syntax we are actually pretending for the compiler to use them. So if it doesn't make sense, you can safely ignore those lines for now. And here we just have a condition to check if the input buffer is valid or not, but normally we should consider that it's valid, but this condition is still good here. But in normal cases, it will go here. So that is to say, the most principal part of our function is those 5 lines. Indeed, we have, in our case at least, 44,100 samples per second, and each buffer will have 120 frames, which means that in a normal case, every second, this callback, thus this loop, will be called 344 times a second. And each time we will loop from 0 to 127 to actually process the inputs and turn it into the output buffer. Here we have small specificities of C, and to make it more convenient for most, I will actually translate it to another syntax. But basically, here is a pointer to the start of our array. And in C, we can actually do mathematics with address. It's pointer arithmetics. And here we have the address of the start of our buffer. And by doing plus plus, we are incrementing the address, and we are actually going to the next cell in the array. It's actually convenient here, but to make it easier to read for everyone, we will translate it in something you could see in other languages. For example, this. Let's safely ignore this for now, and now you can imagine that each time we call a callback, we have a buffer of 128 cells. We are iterating through all of them, and the output of I is equal to the input of I first. But there is a small problem with that, is that we don't have only one input channel. We are not in mono. In my case, I'm stereo output and mono input, but you might even be 4 output channel, for instance. So we cannot do just that, because normally, if we were in mono, we will have 128 cells, all of them being mono. But if you are in stereo, your output buffer will actually be 256 cells, and first cell 0 would be left, then right, then left, then right, then left, then right. And once again, it would be the same if you have 4 output channels. It would be left, right, 2, 3, and etc. So that means that this is not working, because this should be 0, 2, 4, and right should be 1, 3, 5, 7, etc. Which means that for left, we should do this, and for right, we should actually do this. And if you have 4 output channels, you could just do like this, and it will set every output channel to your mono input. And then again, I'm only using mono input, but if you are using stereo input, you should do something like this, of course. But for me, I will go back to this version. If you have a problem with that, please ask me any question in the comments. But for now, we will keep this syntax. Basically, we are filling our left here buffer with a fuzzed version of our input, and our right here is just the normal input without the distortion. But since it's a bit inconvenient, and anyway I'm recording in mono, we will remove that, and we will just say that our right here is actually our left. So left and right channel will have the same value. And we are now filling each of the 256 cells of the buffer. So now, after all of this, we will be able to compile once again and run the program once again. And normally, there is no difference at all. So all of this for this, but now it may be a bit clearer without the pointer arithmetic syntax. But we can go on to the next step. Here we are fuzzing the signal. Let's see how it works. It's actually a macro, a C++ define, a C define, which is calling 4 times a function because it's a cubic amplifier. So this, instead of in our code using this, which would be a bit inconvenient, it's a macro to do this all at once. Now we can try something else. Let's say you want to fuzz it even more. We could try calling it maybe 7 times, of course, matching brackets. And now, if we compile, we can see that it's way more distorted, it's way more fuzzed. And of course, if you only called once cubic amplifier, it will be a tiny bit of fuzz. But it's not really convenient, of course, changing this macro. So we will want to replace this function by doing something, well, exactly this, but not exactly. So let's remove this define, and let's remove this because, yeah, we don't need it. And now let's rename it recursive cubic amplifier. And let's add some parameter, which is, well, it would be strength. Let's call it like that. And we are going to put a loop inside of it that goes from I to strength, which means that we are going to do exactly the same code as before, but instead of calling recursively the function multiple times, we will do it from within the function. So it's not really recursive in itself, but it's iterative actually. And now we still need to do input equal output, because here, of course, we are using the input, and each time we are going back to the start of the loop, we need the new output to be the input. And after 4 iterations or 8 iterations, we will return the final output. Now that is done, we cannot use Fuzz anymore, of course. So we will call recursive cubic amplifier and pass it the number 4. It should be exactly the same as before, because if it was clear enough, we are, instead of calling 4 times the cubic amplifier function, we are calling it once, but inside of it, we are iterating 4 times. Perfect, it's the same. Now, if we are using 1 instead of 4, we will have almost no fuzz at all. Really light. And if instead of that we are using 8, we are now having a pretty heavy fuzz. But now we still have a bit of a problem, because it's better than the macro because we don't have to add more function call, but it's not really easy to modify still. In the next part of this series, we will replace it by some variables, and we will add some rotary encoders and plug them to our Raspberry Pi and find a way to get the input of the rotary encoders in our code, and then we will modify the strength of the fuzz thanks to the encoders. But for now, this video is over, and I will see you in the next video of this second part to actually add a delay to this new pedal we are making.